Hello, guys. Welcome to this live stream. Please, if you can hear me, please consider dropping a comment, saying something so that I would know that you can hear me. Um, yeah, so please use the chat box. Let me know if you can hear me. So, this live stream, I really did not plan on having it. It's just something I decided to do spontaneously. Um, yeah, so it's basically going to be a continuation of so basically I'm still setting up my whole streaming stuff, but basically it's going to be a continuation of the previous live stream we had, where we talked about the tree algorithm, and it's we talked about the tree algorithm and its how to traverse the tree, right, using depth first search. So looking at my screen, we implemented a tree. So we created a basic structure of a node. That's because we said it takes a value, right? And it has like, you know, pointers. So we call them left and right, right? Then we went ahead to, you know, create a function that we'll use to create a node, right? I'm using the implementation keyword and stuff. So we created a function, then we wrote code to pre-order, right? I used to traverse the tree um, in a pre-order traversal technique. So that's moving from the root to the left to the right. Then we went on to do in order, where we move from the left to the root to the right, and we did post order, where we move from the left to the right to the root, right? So we did all that. Then we went ahead. We added some data to our tree, to our roots, right? We created a root by adding some data. I also showed a structure of that here. And so basically, we then ended up calling each of those functions that does the depth first search for us. That is the in order, pre order, and post order. We ended up doing that in that that was like last week, right? We ended up doing that. So today's live stream is kind of unplanned. So we'll just dive into it and see how far I can push it, right? So many reasons why this is unplanned. First of all, because I don't want to go into why it is unplanned, but had a lot of challenges this week. Nigerians will understand, but had a lot of challenges, and for that reason, I couldn't stream on Tuesday. I couldn't stream yesterday on Thursday, but I just decided, oh, let me go ahead and do this thing today, right? What's the worst thing that can happen? Yeah, so that's basically it. If you need a refresher on what we are going to be doing today, please you can go back to the previous stream that I did that talks about depth first search and how to create a tree in in Rust. So today we are going to be looking at breadth first search, right? So as usual, I always pull up Wikipedia and use it as an example, or like where we read about how these things are being implemented, and basically dive into it. But first off, right, um, depth first search, like I said, it has three types, right? Moves from the roots to the left to the right. Then you have the left to the root to the right, and you have the left, right, and root. But in the case of breadth first search, it's based on layers, right? So we move from layers, right? Basically, you can say level by level, right? So this stream is going to be very, very. It's not going to be that long. I guess that's the reason why I decided to do it, because it's not. Guys, please confirm if you can hear me. I don't know, but people are incredibly silent today. So please confirm if you can hear me. Please consider leaving a comment. I don't know why. I don't know if it's bots that are on my live stream most times. People don't usually comment. I don't know why. Um, um, Should have to leave a tweet about that. Anyways, guys, please, I don't know. I just had to make a tweet about people not commenting on. I don't know what happens. People rarely comment, uh, you know, on my streams. I don't know what I did to you guys. Please leave a comment. If you can hear me, you can just say hi and consider asking questions in the chat box. And tomorrow, we'll be having more elaborate live streams. And yeah, so let's just go on. To be honest, I don't know why people don't comment on these streams. I don't know. Anyways, so as I was saying, we are going to be talking about breadth-first search. So basically, from Wikipedia, right? Breadth-first search is an algorithm for, you know, searching a tree data structure for a node that satisfies a given property. It starts at the root. The root is the first one, and explores all node at the present depth, right? Prior to moving on to the node at the next depth level. So this is just like big grammar, like big English. Basically, what is happening here is looking at this diagram here, right? It's going from level to level, right? So you see is the first part, second part, the third part, and the last one. So it's not like dead first parts where you have moving from left, then to the root, then the right, then left root right, left root right, or you have left right roots, left right roots. No, it's not that way, right? This one goes level by level by level by level, right? That's how it's essentially or basically works, right? It moves from one level to another, basically. So, what's the reductions in tree? Okay. Hmm. Um. So, yeah. So basically, and this is just an animated example of Bedford search. Black is the explored area. Gray is queued to be explored later. Right. So this is like using how they use BFS on a maze solving algorithm, right, to find paths, right? So you see how they are looking for paths, to solve the shortest path or something, right? So then it goes on to say, for example, in a chess endgame, a chess engine may build the game tree from the current position by applying all possible moves and using the breadth first search to find a win position for whites. Implicit trees, such as game trees or other problem solving trees, may be infinite size. Breadth first search is guaranteed to find a solution node if one exists. In contrast, plain this one now is talking about depth first search, right? Which explores the node branch as far as possible before backtracking and expanding other node, may get lost in an infinite branch and never make it to the solution node. Iterative deepening and depth first search avoids the latter drawback at the price of exploring the tree's top parts over and over again. On the other hand, both depth first algorithms typically require far less extra memory than the breadth first search, right? And so basically, it's saying that DFS requires less memory than BFS. Breadth search can be generalized to both undirected um, and directed graphs with a given start node, in brackets, something referred to as a search key. In state space search, in artificial intelligence, repeated searches of vertices are often allowed, while in theoretical analysis of algorithm based on best first search, precautions are typically taken to prevent repetition, yada 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 yada. So it goes on and on and on. Then it shows some you know pseudocode and goes on. So these are more details about it. So you can basically gig into this, right? It even goes into the time complexity and completeness, BFS ordering, where you can apply it. So, for instance, the application, some people would say, what's the purpose of learning data structures and algorithms, right? This is it here, right? It has applications. So you said breadth first search can be used to solve many problems in graph theory. For example, copying garbage collection and then Cheney algorithm, right? You can go into this, right? So garbage collection is is something that is available in most languages like JavaScript and all that, right? So it's a form of automatic memory management. And the garbage collector attempts to reclaim memory that was allocated by the program, but is no longer referenced. Such memory is called garbage. Garbage collection was invented. Where's that stuff again? By an American computer, blah, 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 and goes on and on and on. You can read that. So, but for languages like Rust, we don't have anything like a garbage collector, right? Rust has its own ways of doing things that makes it unique. So, yes. What else? So it goes on to say, um, that you can use it for finding the shortest path between nodes U and V, right? With path length measured by number of edges, an advantage over DFS search, right? There's so many ways. So you have the Ford-Fluxing method for computing the maximum flow in a flow network. You have serialization and deserialization of a binary tree versus serialization in sorted order. Allows the tree to be reconstructed in an efficient manner. Construction of the failure function of Ashok, whatever pattern matcher. It goes on and on and on. And I'm sure that if you make further research on this, you'd see quite a number of applications for this particular stuff. So yeah, these things have applications, right? In one of our streams, we implement an undo and redo functionality. And this undo and redo functionality would basically will build on the knowledge of what we did using implementing a stack, right? So we had implemented a stack in one of our past streams. This is it. So we had implemented a stack. So we'll use this stack algorithm to implement the undo and redo functionality that you see in most applications like MS Word, even VS Code itself, right? Your Word documents and stuff like that, right? How you undo and redo stuff, how we add to the stack. We have like two stacks, I don't want to digress so much, but you have two stacks. You add to this one for undo, you pop from this and add to this for redo, just back and forth, right? It is nowhere compared to the actual undo and redo functionality, but it kind of gives an idea of the application for stack. Down the line, I will still think about how we can application of trees or what we can implement in the shortest amount of time, just to give a better understanding of why these algorithms are important, why you should know them, why we should learn them, and yeah. So we'll just dive into it. Like I said, BFS explores nodes level by level, right? Unlike DFS, which uses recursion, BFS relies on queues, for implementation. So we'll use the what's it called? The vecdq coming from Rust to create a queue, right? We get it from the standard library in the collections. Then there we'll be able to get the vecdq. So then after that, we'll be able to, instantiate a new queue and write some code and use some while loops and let some and stuff. Just do some basic pop fronts, right? And pushback implementation that we have done. And all these things, I think we've even used something like this when we talked about, was it three? I think we implemented stacks. I've used linked lists. Yeah, so in our linked list implementation, yeah, so I think I don't have that code here, but I know we did it such that we used the instead of manually building out the linked list. I've forgotten, but I think we did that. I can't really remember, but we did that where we used all those methods. So without further ado, I'll just go ahead and get started, right? So down here, I would add a function, and this function I will call it. So because we are doing bird first search, so I'll add an elaborate comment there. I'll call it BFS. And then, so BFS is for bread. Bread, okay. Bread. What am I doing? breadth first. What's happening? FIRST breadth first search. There's usually a hyphen in between these two guys. Exactly. So we'll write our function here, right? So we just create a function and then we'll just call it BFS trav. So I don't have strength to write out the full thing. So BFS trav, and okay, this BFS trav will take two things, right? Similar to how our in order, post order and whatever functions worked. Okay, sorry, I think I need to declare this in our implementation block. Sorry, that was a funny mistake. Cut this out. Put that comment here. All right. So in this place, we're going to take similar to what we have here. So we just take a root. We need the root, and we need an array, right? So that array we're going to call it result, right? So I'll just copy that guy because, man, I'm tired. I'm not actually tired. I'm just being lazy today. So copy this and paste it here. So basically, what we did here is this is the root, and then um, we are, this is an option, and we are wrapping it in the tree node, blah blah blah, with a generic of t. Then we have our mutable reference to a vector, which can take any value at all, right? It can either be a boolean, integer, whatever, right? But in this our case, it's going to be an integer, right? So that's what this is. It's just like basic TypeScript, right? Well, this is more elaborate and 100% better. Um, you know, yeah. So we have that an option for what's like an option where we wrap the tree in an option so we can handle the case whereby we are expecting a value from the roots, right? So in a case where we get a value, we'd handle it with some. In case whereby we don't get a value, we'd silently panic and return none, right? Without crashing the program. So what I do is at the top here, I need to get our queue. So I always like to reference the documentation, right, in these things. So I would go to vec dq rust. So check this, and here you see that in the standard library in collections we have vec dq, and they say is a double-ended queue implemented with growable ring buffers, right? There are a lot of theories on this ring buffer. I'm not going to go into that. But basically, it goes ahead to say the default usage of this type as queue is to use the pushback, which you use to add to the queue, and pop front to remove from the queue. Right? Then you have extend and append to push onto the back in this manner and all that, blah blah blah. But basically, this is what we are going to put in our program, right? So we're going to go into standard library into collections and we get vec queue, right? So we're going to use this already created queue here. So back in the code, so I'll say use std and collections, and in there I want to get my vec vdq. So this guy, right? Let me check out I'm correct here. So I need my semicolon. Okay. So now that I have that, back to our function, we now need to do some instantiation. So I don't like my code not being formatted. So I always use cargo fmt to format it. So if you take a look, you'll see that this guy is weird. I'll just do cargo fmt and have everything formatted. Exactly. So next thing we're going to do, we're going to create a queue, right? So we're going to instantiate a queue. And how we do this is by using the guy we just imported into the program, right? This guy here. So everything is kind of linked, right? I'm trying to make sure that you see the process and everything. So we'll say let's it should be mutable, and we'll call it a queue, queue, and here we'll then say vec queue. So vec queue. Let me go to the top. Vec dq, not d. Vec dq and new, right? So we use this to instantiate a new queue, right, for our breadth first search. So now, first thing we want to do is to handle the parts where we get the roots, right? And then push a node into it, right? So we want to push back based on what they said here. So push back is to add to the queue, right? So we want to push a node into the queue. So the first thing we'll do is we say if let's, in case you don't understand how the if let works, we made a live stream last week on pattern matching and some other things, right? And this was one of the things we talked about, the if let and how it works, right? So say if let and sum, because remember we wrapped. Okay, so first off, I'll take this out, right? Because I'm trying to go through this step by step, right? So we don't just rush and and everything is confusing. So the first thing is, first off, I want to from the root, right? This root I want to do something. So this root I want to do something here. So I want to like push the node into the queue, right? And I'm going to get the node from this root, right? So now I'm now going to say if let's, right? If let's then sum. So I'm handling it because I know my root here on line 49, the tree node, right? At the top here, the tree node is wrapped in option. So that gives me access to sum, right? So if I hover over this, you can see it's an enum with none and sum, right? So I use sum to handle the part where we get a value, right? So I'll wrap this here. I'll say node. Okay, and I would say is equals to root, right? So here I then want to push into the queue, and how I will do this is because remember I said on the queue itself, right? We have the pushback. So let's go. Let's look at this. Let's look for P. This is pushback. So look at that guy. So here they instantiated a new queue and they called it buff, right? After they've imported, and they are saying buff dot pushback and they pushed back one. So what I'm going to do now, I'm going to say q dot pushback and I'll push the node which is coming from sum, right? Which I've kind of like destructured from sum, if that makes sense, right? Yeah. So back to this place, I would then say q dot pushback, right? Pushback, and I'll pass in my node. So this is the node, right? So say node. And after that, okay, see pop back, push back, not pop back, push back. Exactly. So save this. And yeah, so we've done that part. So next we'll go ahead. Like I said, this stream is going to be really short. It's not going to be one of those elaborate stream where where I would have to stay on the call on where I would have to stay live for hours. I'm so used to Zoom meetings and stuff. I don't even know when I say call. But back to what we are saying. So next, we want to handle the case whereby where we pop from the front. So now, what we are trying to do at this point is we want to remove nodes from the front of the queue, right? So we want to remove nodes from the front of the queue. Then what we just did here was to add a node to the back of the queue, right? So the next thing we're going to do, we are going to pop from it, which is removing nodes from the back, and we're going to use some things like asref, right? And so both what asref will do is it will convert our option, which our three node, which we wrapped with box and finally wrapped with option, is going to convert it to an option that is a reference to the tree node, right? This will enable us to be able to borrow child nodes without taking complete ownership of the child. This is a complex. It's not complex. It is quite glaring to understand this aspect, unless you go and read about borrowing and ownership rights in Rust. And so there is ownership in Rust. Let me see if I would see any. So there is like a complete section in the Rust book that talks about borrowing ownership rights in Rust, and it really explains everything, right, that I just talked about. So you can check that out if you want to learn more about ownership in Rust. But I'll just go ahead and continue with my implementation. So next, I'm going to first of all, I want to pop from the front. So I'll say q dot pop front, and in this place I'll do some things. But before that, I have to first of all use a while loop to, because I want to. This is like, it's going to be like a continuous process, right? Because remember, we are going from level to level, right? So I would say while, I'll say let some node goes to pop front, exactly. All right, so I'll delete this, don't need that. So in here, I would then say whatever, hold on, okay. Okay. Need to check something. All right, so on track. So the next thing I want to do at this point is I want to first of all, right, push into our array. That is our result. If you remember, right, you might not know where this result is coming from, but we had initially declared something like that here, right, in our last stream, right, where because we are just basically building on what we had already done in our previous stream, right? We're just building on that. So we had initially created a vector, and so this vector is what we would pass into our BFS function. So now we want to push what we have come, like what the values we've come across, right? But we don't want to take ownership of it, so we'll just clone it and push a clone of it onto the the vector. The vectors are kind of like arrays, but the only difference is that they take only unique values, right? It must only be integers, or either it's booleans or string slices or stuff, right? It cannot take integers and string slices at the same time. So next we are going to say, so we have results, and our result we know is a vector, and we have the push method. So we'll say push. So it's kind of like similar to the way it is in JavaScript, if you're familiar with JavaScript. So now we know we want the node dot value. So I want to push that value dot clone. So we'll clone it, and yeah, so we'll do that. Results. Save. Cannot find the value of node. What's happening? Oh, I see. Okay, so this, cut this, and just made a very, very funny mistake. I'm supposed to put that here. Okay. Exactly. So sorry, that was a very silly mistake, right? So it's supposed to be in the while loop. So while let sum, so this is the node. So we know that this node we have it refers to the tree node, and this is our tree node, right? And we have the value. So whatever that value is, we don't want to take ownership of it. We want to clone it, right? We want to clone it and pass it into our results, right? So that we can be able to still reuse those values or still revisit them. Because if we completely or outrightly clone it, take ownership of it, we'll not be able to revisit them again, right? So guys, I'm kind of distracted. Please forgive me. It's Twitter. Okay. Okay. All right, back to you guys. So next, where was I? Okay, so we've we've visited the first value, we've pushed it into our results, right? Remember I said this thing goes level by level, right? So to be the root, then next to be the next level, the next level, and the next level, right? The next thing we're going to do is we are then going to say let's visit the left side, right? Because we're going to move from the left to the right, right? So we're going to move like this. Then we'll come to the next level, we'll move like this again, right? I'm trying to demonstrate the whole thing. So if you go back to Wikipedia, so you take a look at this diagram here. You see how we are visiting the first value, which is the root. We'll move from the left. On the next level, we'll move from the left to the right. The next level, we'll move from the left to the right. So that's basically what we are doing here, right? So we'll just use an if let to get the value, which is going to be left because we are going to visit the reference to the node left, and it will make sense when I write the code, right? At the end of it, we'll push back, right, and take a reference of it so we don't completely take ownership of that value and push it into our queue. So when we push it into our queue, when the while loop runs again, that node will then be pushed into the results, right? So it would make sense once I write the code. So let's just go ahead. So I'll say if let, because we're moving from left to right, so we'll say sum, and here we'll pass in the left, left, and then we'll check for reference to want to get the node dot left. Remember, in our node we have both left and right, right? We have both left and right values. So basically it's going to be like these are the left values, right? These guys are left here, these guys are left, these guys are right. So we have left, and then in that place we want to then do our queue. So we want to push it into the queue. So queue dot pushback. So in that place we want to pass our left. So the particular guy that we just want to pass it as ref. So say left dot as ref. So what this as ref does, let's even see pop. Why am I always writing pop? Push, for Christ's sake. Push it in there. So as ref, let's look at what as ref does. Is that stuff? Oh, I'm looking at the. Hold on, hold up. Say as ref. Okay, so this is what I'm looking for. Yes, ref rusts. What's the difference between asref, sample of asref? What's the difference between asref and this? So asref is a trait which is used to reference to reference conversion. I think it's also do the same. Okay. So asref in std. So let's just look at this, right? This is just me trying to drill down into what asref is. So I guess it's the same thing as using as doing what I did here. So trying to touch on all these things, so the more you're familiar with this, the better you get, the less surprised you'll be when you see it in people's codes. So we have this kind of thing here. So the and sign here, right? It's kind of like, let me increase this stuff. So take a look at this guy here, this sign here. It's reference, right? In Rust, reference something. So reference is like the actual meaning of reference. Like this is a reference to a document. So that's what this is, like a reference to another value that belongs to someone else, right? So we represent that with the and sign. So possibly the asref might mean the same thing. I don't know. I'm trying to find out the meaning. So let's go back to this. So it says, this person says, what's the difference between asref, a method, and the and symbol, right? So I know asref is a trait which is used for reference to reference conversion. I think with the and also can do the same. In that case, what exactly is the use case of asref? When to use and when to use asref? I was trying below code and it gave me an error online, blah, blah, blah. Okay. So this person says this sign does that via deref coercions. Okay. That works only for things that implement the deref traits. This person says to answer question 3, the trait asref is implemented for strings. Cool. For multiple output types, as indicated by the error message. Rust cannot infer which type is blah, blah, blah. A lot of answers here. Different option where gives this and asref gives you much more useful. Oh, okay, I see. So I think this one is beginning to make sense. Gives you much more useful reference to the options, and there is reference to the value which is wrapped with an option. Oh, that makes sense. That makes a lot of sense, because I remember I said before that we used asref, right, to convert the 3 node that was wrapped in a box and wrapped in an option. right? So if I come back here, so we have it here, right? So this is our tree node, which represents the left, um, the values that will be on the left, or whatever is being pointed. Like this is the pointer that points to the value on the left and the one on the right. So this using as ref gives us option, which is a reference to the tree node, right? So that we can borrow the child without taking ownership of it, right? And that's exactly what this person is trying to say here, and that makes a lot of sense. Wow. Cornel, thank you for your answer, even if I don't know you personally. Thank you for that. Anyways, let's not digress too far. If you really want to dive deep into that, Rust has a lot of moving parts, right? Um, I for one, I'm still learning the language. It's learning doesn't end, right? So, if you're really interested in drilling deep into how as ref works and normal dereference or reference works, you can definitely go back and do some googling, do whatever it is that you can to understand what is happening here. But basically, this is it, right? This is basically it. This is everything. So the remaining thing now is just to copy. What have I done? Okay, just to copy this guy and duplicate him for the right. So I'll just say this one is RIGHT, and I want to go to the right, RIGHT, and I want to push the right, RIGHT. And that's basically everything, right? Everything is done. So we have the right, note.right, queue, pushback, and we've done everything, right? But the next thing we'll do is just to go ahead. So basically, this is how we implement Brett's first search in Rust, right? First off, you have to use the vector queue, which is a queue that is coming from the Rust itself. You can implement your own queue and, of course, use it. We've done that in our past, some of our past, um, you know, um, live streams. We did that, but I don't think I can see that code here. But I know we did that in that live stream. If you go back to the live stream, you see it. We did it manually, right? You can do that, but this is more efficient. The VecDQ is more efficient, right? Because it's implemented. I think the ring buffer. So, I think I'll say, why is VecDQ more efficient? Let me just check this. Yeah, so exactly. So I said something about the ring buffers, right? So they said a VecDQ in Rust is considered more efficient for operations like adding or removing elements from the front or the back of collections because it functions as a ring buffer, right? Allowing for constant time, which is O of 1, which is very fast, insertion and deletion at either ends, right? So because of this implementation of the ring buffer, that allows it to run at constant time, right? So you can go ahead and implement your own vectors using your own queues using a vector, but it is nowhere going to be as efficient as the vecdq, right? That is automatically implemented unless you want to implement your own ring buffers on it. And why would you do that? Why would you want to invent the wheel when you already have something that works, right? So it's always nice to check these things out, right? To try, kind of converse through the whole process, understand what is happening, basically just drill deep into these things to get you know deeper concepts and deeper understanding of why you should do this against doing that, right? So yeah, basically, we did that in one of our previous streams. So what we did here, we used the vecdq, and then we um, you know initiated it here or instantiated it, and we created the roots. We pushed the roots into the queue. Then we used while loop to move from the left to the right, from level to level, right? And at each time we pushed into our results vector, right? So that's basically it. The only thing we are going to do now is we are now going to try to use it, right? So here I would still do my result.clear. So just to clear out any nonsense that would be in it. So our tree that we already have here would still work, right? So I kind of created this diagram from our last stream. So this tree will still work because here I created the root of the tree. I passed 10 to it. Then I created the root left, which I passed 20, the root right, I passed 30. Then the roots under the roots left, right, under this guy, we created the root right and root left. So if you look at it, you see this is root left as mute, and we did like an unwrap, and you say dot left. So this value was appended to the left side of the tree. So looking at the diagram, you see that it was appended to this side, right? To this side of, so the left part, which is under 20. So if I wanted to do something like this for 30, which is on the right, I will say root right, dot as mute, dot unwrap, then I'll go to the left, I'll do root right as mute, dot unwrap, and I'll go to the right. So it keeps going on and on and on that way, basically. Yeah. So first off, I'll clear that. Then I would call my function. So it's BFS, right? BFS trav. Yeah, I cannot write the actual. Okay. So I remember I did 3 node. So 3 node, and there is BFS trav, and there I would pass in the roots. So the roots, which is this guy here. So I'll wrap it in sum, and here I'll pass in my roots, reference to the roots. Okay, and then I'll pass a mutable reference to the results. So mute reference to the results, right? Then after that, I'll just copy this guy and print it. I have strength. So I'll just put this here and I'll call it BFS. This is going to be called BFS, and that's pretty much it, right? That's everything we need. So just to have a clean working, anyways, let's just leave it like that, right? So I will be able to compare between what is happening in pre-order, in order, and post-order, right? So so you would see that for BFS would have 10, 20, 30, 40, 50, right? It will go in because we are going on different levels, right? It's not as if it did an order, and it's just that it's moving from level to level to level, right? So let's run this code. So cargo run. Let's see if everything works fine. No complaints. So yeah, so we have this, right? So just go ahead and zoom into this guy. I don't need the side terminal, so Command B, close that, and Command plus to zoom in, zoom in, zoom in. And here you can see that we have, so for the pre-order, right? I think this is too large, so we can't even see our tree again. So we have, okay, this is our tree, right? So this is our tree. It's too large. Let me reduce it. So okay, so we have this. So we have so for the pre-order, we are not concerned with what is happening in pre-order, in order, post-order, with the whole DFS stuff, right? I just focused on the BFS, and like I said, it's moving from 10 to 20 to 30 to 40 to 50, right? So that's why we can see 10, 20, 30, 40, 50 for pre-order. And in pre-order, we know that we move from left to the root to the right? So if you take a look at it, you will see that we have, let's look at that again. Let me be absolutely sure of what I'm saying actually. Yeah, so left to the root to the right for, oh, sorry, that's for in order, right? That's for in order, not for pre-order. So, okay, root, sorry, from the root to the left to the right. These things are fucking confusing sometimes. Sorry for that. Okay, I think I made a tweet about this, how I remember them, and imagine I've even forgotten. Anyways, so for the pre-order, we move from the roots and our roots. So we move from roots left and right. So if you look at this guy, so this is the root, right? 10. So that's why we have 10 here. Then we went to the left, which is 20, right? We'll go down again to the left, which is 40 until we've that's why it's depth first. So it goes down that depth. Then we'll go to the right, which is 40. Then we explore this part, which is 30. So this is for pre-order. Right. Then we have the in order, which goes from the left to the root to the right. So if you look at it, we have in order, we have the leftmost one. So we'll visit 40, the leftmost one. Then next we'll visit the second leftmost one, which is 20, right? Then we visit 50. So remember, left, root, right. right? Then the next thing we'll visit is the root again, because we don't have any other one on the left. So we'll go to the root and then the right. So that's why we have this here, right? Then this one for the last one, which is post order, we go from left, right, and root, right? So we have left, so we have 10, then we have 50, which is the one on the rightmost one. Then we go to 20. From 20, we go to 30, which is right again, and we go to 40, right? Then for breadth first search, which goes from level to level to level, that's why we have 10 as the first guy here, 20 as the second guy, 30 as the third guy, and we have 40 and 50 as the last. So guys, that's basically it. I think this should be my shortest stream. I'm about 52 minutes, I'll say basically 55 minutes, right? Yeah, this stream wasn't planned. I didn't plan to do this today. There are a lot of factors that prevented me from having a stream this week, but I'll still be here tomorrow with you guys, 11 by 11 p.m., 11 a.m. Sorry, where we'll talk about just functions in Rust. Right, this is directly from Rust by example, the series that we are currently going to. We'll talk about functions in depth. Right, we'll talk about closures. We'll talk about higher order functions. We'll really drill down into functions in Rust, try to understand every place and why I use things like fn, right? What fn does. So it's just the way you should create a function in the language, right? Then we also look at functions that you can pass as arguments to other methods and stuff, right? Closures, in other words, kind of like similar to arrow functions in JavaScript if you're coming from a JavaScript background. So guys, yes, there you have it. We've finally, I finally kept my word, right, of coming back to breakfast search, and because it's easy for me to just overlook this thing and just move on. Nobody will remember, but I just took it on myself to do this today with you guys, and it was really fun doing this. You can always come back to this video to geek away and try and understand. You can even read it on your own. They can be very complex, but practice over time makes one better, right? Like I always say, we're all learning. No one knows it all at the end of the day, but at the end of the day, practice makes perfect in whatever it is that we are doing. So guys, thank you so much for joining me on this one, and I'll see you guys tomorrow. Good night. Cheers. Peace. Bye.